Yeah, thank you very much for the kind introduction. Good afternoon, ladies and gentlemen. The title is announced, and you may ask yourself, why does he write agriculture and point of care on one slide? What do these applications have to do with each other? And the answer is they both need spectrometer modules that are compact, robust, very stable, transferable, and last not least, are cost efficient. And I will give a few examples where such spectrometer modules are used in these applications and how we address the points that I just mentioned. As we are a first-time exhibitor on this show, I want to say a few words about our company. Ibsen Photonics was founded 31 years ago in Denmark, still located close to Copenhagen, and founded with the goal of developing production technology for transmission gratings in fused silica glass. And after a few years, we also decided to move into the design and manufacturing of OEM spectrometer modules based on this grating technology. So today we produce more than 40,000 transmission gratings. They are very highly efficient, highly stable, and enable compact designs. And if you compare that to the number of 8,500 modules, spectrometer modules that we produce per year, you will see that there's a difference. And we also sell the gratings in other markets, like for face masks. Yeah, okay. It's face masks, laser pulse compression gratings, and other applications. Okay, now we have the right slide also on the screen. Okay. And right now we have about 85 people, strongly growing. So if you're interested in working for a spectrometer company, have a look at our website. As we are only focused on the modules themselves, we also focus with a strong team on the design and development of these modules. That is based on the fused silica substrate, the wavelength range that we can cover, so around about from 175 nanometer up to 2.5 microns. And on the left-hand side, you see the 5 standard platforms that we have in our portfolio these days. They decrease downwards in size, and you can see how the different families, the different platforms cover the spectral range that I just mentioned. And of course, there are numerous application areas where nowadays spectroscopy is used for analytical purposes. So the outline of this presentation will be a few examples from agriculture and point of care. I will talk about the benefits of visible and near spectroscopy, explain the challenges that are associated with these, and then shortly mention the components of a spectrometer system, and introduce to you the Pebble Platform, which is the most recent one and the smallest one that we have designed. And actually what I have here in my hand, that is a complete spectrometer. And it's very powerful, as you will see later on in the presentation. And I will give my point of view why we think that Pebble is ideal for these two application areas. Here are some selected examples where spectroscopy can be used. It can be used for the measurement of the solar irradiance and reflectance for agriculture in the field. You can use it for control and detection of the artificial lighting in greenhouses. NIR spectroscopy is routinely used for analyzing moisture, fat, and other food constituents. Raman spectroscopy, fluorescence spectroscopy are used to detect trace levels of pesticides, for example, adulterants in products that shouldn't be there, and other contaminants in food products. They can be used for grading of food and vegetable, or just simply checking for color in a process line. And for a point of care, it's very often used for blood analysis for different types of diseases and viruses. Here's the first example from agriculture. You can see an arm, and on that arm, an array of spectrometer modules is used to give an online feedback on a tractor system about the either soil quality or the status of the plants on the field. And that information later on can be used to locally spray or to add fertilizer to the field. It's also used in NIR spectroscopy to assess the quality, the type of soil, and decide where you need to fertilize, or in general where to put which plant for the most effective growth. Smart farming, precision farming becomes very attractive, popular in the recent years, and of course you need artificial lighting for that. And as it is known, different light conditions, different wavelengths have different impacts also on depending on the types of species that you're using them for. So you want to know and control what is the spectral content of the light that you illuminate your plants with. Then spectroscopy is used in transmittance mode, for example, to look inside a produce, to check it for internal rot that you can't see from the outside, to determine the Brix value, the dry matter content, acidity, and ripeness, for example. And last but not least, one example from point of care, where it is used, for example, for blood analysis of erythrocytes, hemoglobin content, and hematocrit count. Of course, it can be used for detection of sepsis with CRP in human blood samples. And there it's very important that the spectrometer works very stable, because you're looking at very fine details and shifts of the measured spectrum. And it can be used, for example, for fungicide detection in other samples, can also be blood, where fungicide, of course, shouldn't appear. And an example that I haven't prepared as a slide, but of course, in COVID times, you all know that PCR is used for COVID detection, and very often that is also used for spectroscopic technologies. So, what are the key challenges in all these applications? If you want to design an instrument that is used in the field, on a tractor, on a machine, or used in changing conditions like in point of care, where you can't control it in an environment like a lab, you want to have a stable spectrometer and instrument, and it also needs to be transferable. What does that mean? Stability means, of course, that the instrument that you have should be stable in the sense that the performance does not change when the unit is exposed to changing environmental conditions like temperature, vibrations, shock. And that means that especially the optical module in your instrument needs to be very stable mechanically and thermally to deliver the same results all the time. Transferability is another important point. If you have, for example, distributed sensors and you need to exchange sensors from time to time, that no matter which unit with a specific serial number you use, the results that you achieve are still the same. That is especially important if you use post-processing methods like chemometrics that really depend on the same spectral signal for the same content. And for the spectrometer in question, it means that you need to have a very low unit-to-unit variation of the resolution and also of the peak shape, because these are main parameters that are relevant for chemometric post-processing. So the key components of spectrometer systems are, of course, a light source or natural lighting sometimes. Need some optics to collect your signal. Then you have the module, that could be one of ours. And last but not least, of course, every day in all applications you have some software to really extract the information that you need, because the farmer on the field doesn't want to look at a spectrum. He wants to have a qualitative or quantitative information and some help of what to do. So to address these needs, we have developed the Pebble Platform that I showed you. It's available in 3 different variants. It comes as a WIS spectrometer covering 360 to 830 nanometer. So it's not only what we as humans consider really as visible, but it also fulfills the requirements of some industries that say, okay, to really fully characterize light and, for example, printed matter and LEDs, whatever, we need a somewhat extended spectrum that we have shown here on the slide. Although the spectrometer is very small, it has a high numerical aperture, so you can collect a lot of light. So it's still very sensitive. And we have chosen a compromise of 6 nanometer resolution, which is fully efficient for a lot of applications. Then we have chosen a detector that has 256 pixels, channels if you will, because more pixels probably wouldn't make sense anyway with the optical setup. And the footprint that you can see is roughly 2 cubic centimeters, so it's really very compact. So what you see, the black part is the optical bench itself, and then the SMA connector is almost as large as the spectrometer, and then we have the small readout electronics and control board. But of course, it can be very fast because of the low number of pixels, so you can read out a spectrometer with almost 5 kilohertz. Then we have a very similar version for the NIR, so that can be used then for agriculture, for example, red hat detection measurements, where the wavelength range is shifted to 500 to 1100 nanometer. And last not least, we have a NIR version, which works up to 1700 nanometer, where a lot of molecular fingerprints are detectable. So it's quite useful for advanced spectroscopic molecular detection. Otherwise, same parameters, resolution still 12 nanometers, which is sufficient for most applications. And we use an in-gas detector here, of course, with 128 pixels, which also allows a very high frame rate of 3 kilohertz. So the common points about these 3 models are, as you can see, it's very compact. It's highly sensitive because of the large numerical aperture. They offer a high frame rate, so you can really take many measurements per second. It's environmentally stable, and they have a very low unit-to-unit variation. So how do we achieve that? How do we address these 2 points? Transferability. We are focused on making stable OEM designs, so we do not really offer complete spectrometer systems. So all our effort goes into the module, making it stable. And as I've mentioned, we use our own transmission gratings for all our spectrometers. And this specific spectrometer also uses transmission optics, that is lenses as collimation and focusing optics. And that by design inherently makes a very stable instrument, because unlike reflection optics, if you look through a window and you tilt and move the window, your image behind the window will not change. But if you look into a mirror, immediately when that vibrates, your image will change and shift quite a lot. So using only transmission optics by design, these modules are very stable compared to others in the field. Of course, we inspect all our modules with a very tight tolerance and pass and fail criteria in production. So nothing leaves our house that doesn't fulfill the agreed specifications. And last not least, I mentioned chemometrics that relies on symmetrical and consistent peak shapes, is also supported by a transmission optics design, because if you think of a typical Czerny-Turner spectrometer where you need to work in off-angle configurations, there the peaks can be distorted, which is not nice for chemometric applications. Stability, of course, compared to bigger spectrometers. In these designs, in these instruments, there are no moving parts, so it's obviously stable because of that. And as explained in the context of transferability, transmission optics enable a more stable optical design, both thermally and mechanically. And we have experience with that platform for many years. The Pebble is basically the smaller brother of our high-throughput, high-performance spectrometer ROC that has the same optical layout, but just in this version a lot smaller than before. So that's from my side. Thank you very much for your attention. Of course, you can kind of ask questions. You can also see our other spectrometer platforms on our booth, which is down the aisle here on the right-hand side. And now I think we still have time for questions.
Yes, thank you very much. We do have plenty time for questions, which is good. Do we have any? Yes.
Hello. Yeah, one question. So with the Pebble platform, so what aperture sizes are we roughly talking about? I mean, that looks pretty tiny.
So yeah, the numeric aperture is 0.22.
Yeah.
On the slit size, if you're asking for?
Yes, slit size and like the optics and the grating aperture, basically.
Yeah, I mean, it's really amazing. The grating is only 1 millimeter inside. And the slit sizes we work with, there are different configurations. It goes from 25 to 125 micrometer that you can select when you order the spectrometer.
Another one?
Just a follow-up. So it's basically like a slit-based spectrometer with like no collimating optics inside, or do you have any other optical elements inside?
Yeah, there's a collimation lens that collimates the incoming light to make it parallel before it hits the detector, and then there's a focusing lens after the grating to focus it down on the array. Yeah.
Okay, so pretty much like a classical transmission grating setup.
Yeah, it's all transmission optics. Yeah.
Right.
Because they are less failure tolerant, intolerant, I learned, right? In comparison with the mirrors. Or
yeah, they are not. I mean, I always give that example of reflective optics. If they vibrate or shift, also your image will shift actually twice as much with the angle. But if you look through a window and you tilt that window, the image behind that window stays. So even though there would be some movement inside or thermal expansion in such a module, the effect of that would be much less than if you have reflective optics inside, which most spectrometers have. They very often use mirrors as collimation and focusing optics, and they typically also use as gratings, reflection gratings. So here it's by design, by principle, it's much less sensitive to shift, be it mechanical or thermally. Yeah.
So you can put it into more applications actually, and
yeah,
not in a rougher environment maybe.
Yeah, for example, agriculture. If you want to mount a spectrometer module on a tractor, on a harvesting machine, wherever you want to have spectroscopic information, I think reflective optics will have a hard time, and this is much more robust. And then, of course, it's also very compact and small, and also cost efficient compared to more classical, larger optics.
So, yes.
Yeah, thank you. Maybe I missed this, the C reactive protein measurement. So maybe you can show that slide again. So what is the advantage over existing technologies or existing methods?
Yeah. Okay, just a second. I need to go back to you're referring to this one?
Yes.
Yeah, it's nothing that I can claim we would be involved in. And I can't tell you what the detection method really offers as advantage over other detection methods where you have these. You see, there's a chip that is modified on the surface. That's nothing we are involved in, but it's an example where spectroscopy would be used to read the signal from that. But as you can see, there's the source where I picked the information from. It's a very recent article, but the point that I also wanted to make with that one is you can see the change in spectral characteristics is very, very fine, and you can imagine if you have a platform, a spectrometer platform that is not very stable, you wouldn't be able to detect these or would be misleaded in taking instability for physical information.
It's a more robust system, maybe.
Yeah.
Okay, thank you.
Do we have other questions? So you use at some point a material system indium gallium arsenide, right?
Yes.
Is it right now a problem, or do you suffer from like supply problems for this material, or don't you use so much an amount that you would have some problems?
Yeah, I mean, we don't source the raw material itself. We just buy detectors where the material inside is the photosensitive material inside is indium gallium arsenide. But of course, as everybody knows, electronics are an issue these days. But it's no secret. We work with Hamamatsu mostly, and we have a very strong relation to Hamamatsu. So we still have delivery times that are accepted, put it that way.
So just double the normal.
Sorry?
So just double the normal.
Yeah, yeah, probably something like that. I mean, actually, let's say electronic components are the larger challenge right now compared to the sensors themselves. Like simple FPGAs for electronics boards, it's amazing, yeah, difficult to get. So we are designing around that with other components to keep delivery times acceptable. But I think everybody in the audience will have similar experience with electronic components.
Yeah. So we would have time for other questions, so please don't be shy. You can, take the chance.
But otherwise, again, I'm here at the booth down the aisle.
Fine. So I don't see further hands raised at the moment, so thank you again, Dr. Pust.
Thank you.